On April 23, 1987, around 1:30 p.m., the partially completed 16-story L'Ambiance Plaza in Bridgeport, Connecticut collapsed during construction. It became one of the deadliest building disasters in US history. Iron worker Kenny Shepard was stack welding steel wedges under the 9th, 10th and 11th floor slab. He looked away for just a moment to shield his eyes from his partner's welding, and that's when he heard it. A metallic bang followed by rumbling. He looked up and saw the slab above him was cracking like ice under pressure, and then everything gave way. The slab fell, one onto the next. The West Tower crumbled, followed closely by the East Tower. The entire structure came down in about 5 seconds, only 2 seconds longer than a free fall from that height. Kenneth was thrown into the rolling scaffold steel frame, which somehow saved his life. He was the only one from his crew to survive. Despite 8 days of non-stop rescue work, 28 construction workers lost their lives. But what made this collapse so terrifying wasn't just a tragedy, it was no one could immediately explain how a nearly completed building could fall so fast. The L'Ambiance Plaza was a residential project, 13 floors of apartments over 3 levels of parking structure. It had 2 offset rectangular towers, east and west towers, separated by a narrow gap. Each tower measured roughly 19 by 34 meters. The plan was to tie them together at every level with a cast-in-place concrete strip, effectively making them one building. The floors are made of post-tension concrete slabs, thin but strong. This is achieved by laying high-strength steel tendons along the slab before pouring the concrete, and tensioning those tendons after the concrete cures. It compresses the slab, proving its stability to resist tension forces, which is quite common for residential buildings. Nothing new here, but all 16 slabs are cast at the ground level, stacked one on top of the other, and later lifted into place using a technique called the lift-slab method. It was fast, it was efficient, and was widely used until this project. The lift-slab method uses hydraulic jacks mounted on top of the steel columns. Each jack connects to 2 long threaded rods that hook beneath shear heads embedded into the concrete slabs. These shear heads serve 2 purposes. The first is to act as lifting anchors for the jacks, and the second is once the slab is in place, they help transfer the floor weights into the columns. All jacks are controlled by a synchronized console to ensure a level lift, though manual adjustments are often needed, and these slabs are typically lifted in groups of 2 or 3 to preset heights marked by weld blocks. These are steel brackets welded onto the columns. And the way the slab weight is transferred to the columns is by temporary wedges which are inserted between the shear heads and the weld blocks to hold the slab in place. Once the loads are transferred, the wedges are tack welded, not to carry the load but to prevent the wedges from falling during the next lift. Once the slab reaches its final position, the shear heads were permanently welded and grouted. And this is how a typical lifting operation works. During the lift, the jacks extend to lift the slab package. Then these nuts are lowered to hold the slab height. The jacks are reset and these nuts are lowered to lock the jacks. And the jacks extend again while the slab rises to a new height. And so on until the slab reaches its height. The lift slab technique was patented in 1948 and had a really good safety record until this project. But there is a weak point to this entire technique. During construction, the building is extremely vulnerable to lateral forces. These are forces made by wind or sideway loads. This is why taller buildings are usually never constructed using this method. To handle this, shear walls, which are solid concrete walls to resist sideway motions, are supposed to be built. But at the time of the collapse, the West Tower was reported to be more than 6 floors ahead of its shear walls, meaning that the structure had little to no lateral stability. And to add more insult to injury, this wasn't the only problem. The building used 2 types of shear heads. Typical shear heads had cutouts in their lifting angles to prevent columns from shifting off-center. But at the 4 central columns of each tower, they used special shear heads with no such cutouts. This means that there was some degree of freedom for these columns to shift, and the wedges supporting them could become unstable or improperly seated, because one wedge could end up with a bigger gap than the other end. Keep that in mind because all the investigation report findings point out that the collapse started at the West Tower around one of these columns. On the morning of the collapse, workers were lifting the 9th, 10th, and 11th floor slab package into a temporary resting position at level 6. Above it, the 12th floor and roof slab had already been wedged into place, separated by just 200 or 8 inches between those two packages. Iron workers were moving across columns, inserting and welding wedges to transfer the slab load from the jacks to the columns. By lunchtime, the work wasn't complete. And then came a very questionable move. Other workers, for no clear reason, attempted to straighten or plumb the west tower using a 12-ton horizontal hydraulic jack wedged between the top of the east and west towers. In theory, it's supposed to correct a vertical misalignment. In practice, introduced lateral forces into a structure already lacking lateral resistance. Remember, the shear walls at the west tower were lacking 6 floors behind the lift slabs. Meanwhile, not all columns are equal. Some had wedges, others were still hanging on lifting rods. Allegedly, at the time of the collapse, wedges had just been tack welded at column 4.8E, and at column 3.8E wedges were inserted but not yet welded. And then at 1:30 p.m, it happened. The 9th, 10th, and 11th slab package suddenly dropped. It smashed onto the floors below, and the west tower came down. The east tower, connected by the pull strips, followed seconds later. Most survivors and nearby workers agree that the collapse happened too fast and started in the west tower, and it began with a single loud bang. When rescuers arrived, they found both towers had collapsed straight down, mostly within their own footprint. The steel columns were bent inward, toward the center of the towers, which was a clue that the collapse began in the middle and pulled everything inward. The slab shear heads also served as markers, indicating which parts of the building fell first. And 2 columns stood out, column 3E and column 3.8E. Their shear heads had slid the furthest, indicating the collapse likely started at or near those points. So what actually triggered the collapse? There is no definitive answer, but before the collapse there were already red flags. At column 3 and 3.8E, gap distances between the shear heads and weld blocks were significantly larger than they were supposed to be. In some cases, twice the normal size. We are talking very small gaps here, but these gaps matter because the system depends on precisely seated stable wedges. And this is also because of the special shear heads used on these central columns, which lack cutouts that prevent the columns from lateral shifts. With no redundancy and poor alignment, the slabs were barely seated on narrow guide bars. Evidence suggests hydraulic fluid was present at some of these wedges, likely spilled during earlier lifts, reducing friction on already unstable wedges. In this condition, the wedge with the bigger gap is likely rolled out under eccentric load. The collapse sequence may have started like this. At column 3E, one of the 2 support wedges of the 12th floor and roof package rolled out due to lack of stability. Considering the large gap, the shear head now supported only on one wedge, experienced severe eccentric loading. The second wedge slipped due to lateral load experienced by the hydraulic jack. With no support, the 12 and roof slab package fails and drops 200 mm or 8 inches into the 9th, 10th, and 11th slab package. That shock overwhelms the temporary supports below. This causes the lifting nut at column 3E of the 9th, 10th, and 11th slab package to slip out and impact the column, producing the famous bang heard by workers. The lifting nuts dislodge, shear heads ripped from slabs, column buckles inward, and a full vertical progressive collapse begin. And the east tower, which was tied to the west tower, follows. This remains one of the leading theories, but is this what really happened? No one knows for sure. But there are alternate theories. Evidence from the crash site, unfortunately, were inconclusive. Some investigations attribute the failure to column 3.8E, not 3E, partially due to the difficulty of identifying the wedges and shear heads that belong to each column. Another theory discusses post-tensioning layout flaws. Some tendons diverge from columns, especially near the elevator shaft in the West Tower, violating the American Concrete Institute. Post-tensioning tendons are supposed to carry loads to the columns, which doesn't look like it's happening here. There is also a poor welding theory. There are reports of rushed or inconsistent welds on wedges and weld blocks. This may have failed under stress. And there are more theories, but in the end, no single theory could explain it all. But what we know is that it was a series of small issues that compounded in the wrong way at the wrong time. And this shouldn't be this way. We would have understood this incident better if things were handled differently. Within hours after the collapse, TT engineers were brought in by the city of Bridgeport to investigate the collapse. They stayed on site during the rescue and cleanup, and they hired their own specialists to help piece together the incident. And since the building was still under construction, the Occupational Safety and Health Administration, or OSHA, launched a parallel investigation and brought in the National Bureau of Standards, or NBS, now known as NIST, which seems pretty good since we have multiple parties trying to explain the same thing. By September 1987, NBS had released its preliminary report. By October, TT had a working theory and a full-scale testing plan. But in 1989, everything stopped. All lawsuits and OSHA fines were settled out of court. As part of the settlement, the investigations were halted and testing were never complete. The final result, the official cause was never confirmed. Over 100 companies of designers, subcontractors, engineers and developers were pulled into a legal tangle. A two-judge panel negotiated a universal settlement, avoiding what could have been years of courtroom battles. The judgment: widespread negligence, carelessness, sloppy practices, and complacency. No single smoking gun, just layers upon layers of failure in design, construction, and oversight. In total, 20+ parties were held responsible and contributed to a $41 million settlement fund. $30 million went to the families of the 28 workers who died and those who were injured. $7.6 million were used to resolve legal claims between all the involving companies. Before 1987, lift-slab construction had a solid reputation. After L'Ambiance, the reputation gone. Contractors stopped using it, engineers avoided it, and code officials hesitated to approve it. The method wasn't banned, but it became rare. Today, lift-slab used only under strict conditions, with heavy bracing and under tight professional supervision. This wasn't just a building failure, it was a system failure in design, construction, and inspection. But still, the bigger failure is that we're still not 100% sure what happened. Thanks for watching. This was by far one of the most complex videos that I've made. Not because of the technical details, but because of how fragmented the information was. Hundreds of pages, dozens of sources and conflicting theories, and a collapse that still has no answer. But if you found this video interesting and if you've learned something, subscribe and let me know in the comments what should I cover next. And I'll see you in the next video. Bye for now.